Hi everyone. Today we're going to be completing our notes on 12.2 arithmetic sequences. I want to start with this warm-up. Let's find the formula that defines the sequence 1, 4, 7, 10, and so on. We're going to find two different formulas, the explicit formula and the recursive formula. Okay, so to start, I noticed that we can define each of our terms. A1, which is our first term in the sequence, is 1. A2 is our second term in the sequence, which is 4. Our third term is 7, and our fourth term is 10. Okay? So I noticed that each of these terms increase by a common difference of 3. So each time we add 3. So that tells me that our fifth term I would expect to be 13. Now, because we're increasing by a constant, this is similar to a linear function that has a domain of the natural numbers. So the linear function that would model this would have a slope of 3. That's our common difference, or our constant rate of change. In order to write the equation for a linear function, well, we need this, not just the slope, but we also need a point. So the point that we're going to use is our first point. That's going to be the first term of the sequence is 1, and so the first term is our input, and the output is 1. So that would be the first term in the sequence being 1. So defining the linear equation using point-slope form, we get y minus y1 is equal to m times the quantity x minus x1, or we get y minus 1 equals 3 times the quantity x minus 1. And then solving for y, putting in the slope-intercept form, we get y equals 3x minus 2. Using sequence notation, we get an is the output, right? The term in the sequence is equal to 3n minus 2, where n is the number term in the sequence. Okay? If I wanted to find the recursive definition, well, we know we need two things for the recursive definition. We need the starting value, the term, and then we also need the rule. So our starting term is going to be our first term, a1 equals 1, and then our rule, or our formula, an equals the previous term, an minus 1, and then plus our common difference, 3. Okay? Now, if we wanted to go from the recursive definition to the explicit definition, we could do so. I know that an is our function output and n is our function input. So we get, using point-slope form, an minus 1 is equal to our common difference, 3, times the quantity n minus 1, where n minus 1 is or n is the number term in the sequence. Okay? So then solving for an, we get an is equal to 3 times the quantity n minus 1, and then plus 1. So there's a couple things that I noticed about our final answer here, this definition for an arithmetic sequence. This is an explicit definition, so we can plug in any value n into our definition, our formula, and then get any output from that. I also noticed that this plus 1 is our first term. We're going to call that a. So that's our first term in the sequence. Okay, and so that comes from this right here. I also noticed that this scalar multiple here, this multiplying by the grouping here, is our common difference d. So we're going to define that using d. And that's kind of like the slope of a function. That just tells us how much are we changing with each successive term in the sequence. And so this definition here is going to help us find our definition for an arithmetic sequence. All right, so let's go ahead and formalize that. An arithmetic sequence is a sequence in the form a plus d, a plus 2d, a plus 3d, and so on. Okay, so you might notice a pattern here. We've got our first term a, and then every time we're adding another common difference. So adding d, and then adding another d, and then adding another, and so on. Okay, so every successive term, we're adding that common difference in. Okay, so let's go ahead and define these variables, where a is the first term, and d is the common difference of the sequence. Okay, where a is the first term and d is the common difference of the sequence. The nth term, so we can define this using an explicit formula. The nth term of an arithmetic sequence is given by a sub n is equal to our first term a plus the quantity n minus 1 times our common difference d. And so we can see the similarities here from this explicit formula for the nth term of an arithmetic sequence and what we found in our warm-up today. Okay, so that common difference is the number that we're multiplying our grouping n minus 1 by, and then our first term is that constant added or subtracted. Okay. So go ahead and flip the page. Let's try a few examples. Example 1, find the first 5 terms and the nth term of an arithmetic sequence where a equals 2 and d equals 3. Okay, so I know that an arithmetic sequence is in the form a plus d, so 2 plus 3, a plus 2d, so 2 plus 2 times 3, and then 2 plus 2, 3 times 3, I should say, and then 2 plus 4 times 3. And we could keep going, but this gives us our first 5 terms, okay? So our first 5 terms are 2, 5, 8, 11, and 14. To find the nth term, we can just plug this into our definition. A sub n is equal to our first term, 2, plus our common difference, 3, times the quantity n minus 1. Okay? Example 2, find the first 6 terms and the 300th term of the arithmetic sequence. So we know that this is an arithmetic sequence, so that tells us that it's going to follow a common difference between successive terms. Okay, so our first term is going to be 13, and then our common difference, in order to find this algebraically, you can just find the difference between 2 successive terms. So we're going to take our second term minus our first term, 7 minus 13, and that gives us negative 6. So our common difference is negative 6. Our first 6 terms of this sequence then would be 13, 7, 1, negative 5, negative 11, and negative 17. These are the first 6 terms of the sequence. Our 300th term, we can use our explicit definition. So a sub 300 is equal to our first term, 13, plus n minus 1, or 300 minus 1, times our common difference d, so times negative 6. If we were to evaluate this, this is equal to negative 1,781. Okay? So A300 is negative 1781. All right, example 3. Given the arithmetic sequence whose 11th term is 52 and the 19th term is 92, find the 1000th term. Okay, so I know our original definition, A sub n equals A plus the quantity n minus 1 times d. Okay, so let's plug in some values. We know that the 11th term, a sub 11, is 52. And I know that's equal to a times a plus the quantity n minus 1 times d, where n is 11. And then we also know that the 19th term, a sub 19, is equal to 92. And that's also equal to a plus 19 minus 1 times d. So now what we have is a system of linear equations. We have 2 variables, 2 equations. We can solve this. So 52 is equal to a plus 10d, and 92 is equal to a plus 18d. Okay, so this is our system of equations. If we were to solve this, I'll leave that for you. The solution to this system is a equals 2 and d is equal to 5. Okay, so now that we have a and d, we can define our arithmetic sequence. A sub n is equal to 2 plus quantity n minus 1 times 5. Okay, and if I were to evaluate this for the 1000th term, a 1000 is equal to 2 plus 1000 minus 1, and then times 5. This is equal to 4,997. All right. Example 4, find the sum of the first 8 terms of the sequence. Okay, so I know that we have, let's see, 1, 4, 7, 10, 13. The next term, well, if we follow this pattern here, we're going to be adding 3 each time. So I would expect the next term to be 16, and then 19, and then 22. These are the first 8 terms. If I were to add all of these up, this is equal to 92. Okay. Now, what if we were asked to find the first 80 terms? This would be a pretty arduous process to add 3 and find the next term and find the next term. And then how can we find this without adding each term? This would be pretty tedious. Well, go ahead and flip the page. This brings us to partial sums of arithmetic sequences. So given the arithmetic sequence, so for the arithmetic sequence, which we already know is defined by a sub n is equal to a plus the quantity n minus 1 times d, the nth partial sum, so remember the sum of the first n terms, is given by, well, Sn is equal to a plus the second term, a plus d, plus the third term, a plus 2d, and so on, all the way up to the nth term, which is a plus the quantity n minus 1 times d. Remember, that's our definition for an arithmetic sequence. So this is the nth term. So the sum of all of these terms all the way up to the nth term is our Sn, the partial sum for arithmetic sequences. This is given by, there's 2 forms. The first is Sn equals n over 2 times the quantity 2a plus the quantity n minus 1 times d. Okay? So we can see some similarities here between our explicit definition and the nth partial sum. The other representation here is Sn, nth partial sum, is equal to n times the quantity a plus an over 2. And so what's nice about this is our first form, notice that we need 3 things. We need the number of terms, n, we need the first term, and we need the common difference. Okay? Whereas the second representation here, we just need the number of terms, we need the first term, and then we need the explicit definition, a sub n. Okay? Both of these are equivalent, so you can use either of these representations to find the partial sum of an arithmetic sequence. Let's get some practice. So let's try example 5. Find the sum of the first 40 terms of the arithmetic sequence. Okay? So first thing I notice, our first term a is equal to 3. I see that our common difference every time we are adding 4, so it's positive 4. And we want to know the sum of the first 40 terms, so that tells us n is equal to 40. Okay? So let's try both. So using method 1, we have S40, the sum of the first 40 terms, is equal to n over 2, so 40 over 2, times the quantity 2 times a, which is 3, and then plus n minus 1, or 40 minus 1, times our common difference d, which is 4. Okay? So this is equal to, well, we have 20 times 6 plus 39 times 4, which is 156. And so what we get when we evaluate is 3,240. So the sum of the first 40 terms is 3,240. If we were to use method 2, so we need to know the explicit definition. We know that an is equal to the first term, 3, plus the quantity n minus 1, times our common difference d, which is 4. Okay? So plugging it in, S40, partial sum for, or the 40th partial sum, is equal to n, 40, times the quantity, 3, our first term, plus our explicit definition, which we know is 3 plus the quantity 40 minus 1 times 4, and that's all over 2. Okay? So this is equal to 40 times, we get in our numerator, 40 minus 1 is 39 times 4, and then plus 6 is equal to 162. That's all over 2. So this is equal to 40 times 81, which is 3,240. All right, so we can see that we get the same answer either way. Okay? All right, so example 6. Find the sum of the first 50 odd natural numbers. If I were to write this out, we would get 1, 3, 5, 7, 9, and so on. and I don't know what that 50th odd natural number is. Okay, so in order to find that, well, I know that the first term is 1, our common difference is 2, and I know that we're trying to find the sum of the first 50 terms. Well, to find the 50th term, we can use our arithmetic sequence. So to find the 50th term, a50, that's equal to our first term, 1, plus 50 minus the quantity 50 minus 1 times our common difference, d. This is equal to 1 plus 98, and then that's equal to 99. So that tells us that our 50th term is 99. Okay? I'm going to use the second method. Since we already found our explicit definition, to me that seems a little bit easier. So S50 is equal to 50 times the quantity, first term 1, plus our explicit definition, 1 plus the quantity 50 minus 1, times our common difference d2, all over 2. This is equal to 50 times, well, we have 50 minus 1 times 2 is 98, plus 2 is 100 over 2. This is equal to 50 times 50, which is 2,500. All right. Go ahead and flip the page. Let's try a few more. An amphitheater has 50 rows of seats with 30 seats in the first row, 32 seats in the second row, 34 seats in the third row, and so on. Find the total number of seats in the amphitheater. Okay, so I know that the first row has 30 seats. I know that the second row has 32, third row has 34, so our common difference is 2. In each subsequent row, there are 2 additional seats. And I want to know how many seats are in their entire amphitheater where there are 50 rows. So we're trying to find the partial sum S50. All right, so then I know that S50 is equal to, using that first definition, 50 over 2 times the quantity 2 times 30, and then plus the quantity 50 minus 1 times our common difference 2. Okay, so this is equal to 25 times 60 plus 49 times 2 is 98. So this is equal to 3,950 seats. Okay. Example 8, how many terms of the arithmetic sequence 579 must be added to get 572? This is our last problem for today. So I want to know n, how many terms? Okay, so I know that the first term is 5. I know that our common difference is 2. And I want to know how many terms in the sequence do we have to add up in order to get 572. So we know that the partial sum is going to add up to get 572. So that tells me 572 is our partial sum. We're solving for n here. Using that first definition, we have n over 2 times the quantity, 2 times a, or 5, and then plus the quantity n minus 1. Again, we don't know n, times our common difference, d is 2. Okay, so we get 572 is equal to n over 2 times 10 plus 2n minus 2. Okay, well, let's see. We got 572 is equal to, distributing that n over 2, we get 5n, and then plus n squared, and then minus n. Okay, so distributing that n over 2. Subtracting 572 from both sides and combining like terms, we get 0 is equal to n squared plus 4n, and then minus 572. So I combined those n's, and then I subtracted 572 from both sides. Okay, so we're looking for factors of 572 that add to 4. The answer is negative 22 and positive 26. So this factors to n minus 22 and plus 26. And so we get the solutions n equals 22 or n equals negative 26. Now we have to consider which of these solutions we accept. Because we're talking about the number of terms in a sequence, n cannot be a negative 26. Remember, the domain of a sequence is the natural numbers. So we cannot include any negatives or 0 or anything like that, any fractions either. Okay, so let's go ahead and write that out. Since n is the number of terms in the sequence, n cannot equal negative 26. So therefore we accept the solution n equals 22. 22 terms must be added in the sequence in order to get 572. Okay? So these have been our notes on arithmetic sequences. We're going to get a whole lot of practice, so we'll see you tomorrow. Have a great day, everybody. Goodbye.